everyone. Welcome to episode 14 in the op-amp tutorial series, op-amp finite bandwidth part 1. Today we're going to start by going over the typical features of the real open-loop gain transfer function of op-amps by taking away the infinite bandwidth and infinite gain approximations. Then using this we'll show some loop gain transfer functions with some standard resistive feedback networks, and then show how the feedback and loop gain transfer functions translate into closed-loop gains. So finally, we're talking about finite bandwidth of op-amps. We can no longer represent the gain as infinite, or a single finite value for all frequency, instead representing it by the transfer function AVOL of S, which is a function of the Laplace transform variable S, which we recall is equal to j times omega, where omega is the angular frequency of the signal in radians per second, and j is the imaginary number equal to the square root of -1. So, bandwidth is finite, gain is finite, and as in the previous video, we can no longer assume VOP plus equals VOP minus. So now let's take a look at what the Bode plot of a typical op-amp AVOL of S looks like. Here's the Bode plot of the open-loop transfer function of an 808618 op-amp, a fairly low-cost, high-precision CMOS op-amp, good for low-voltage circuits that need DC precision and low input bias current but don't really need great noise performance. Here I've used the model from the popular SPICE program LT-SPICE to plot the open-loop gain. It's important to note that SPICE models are generally not complete, and relying too heavily upon them can cause you problems later, especially if they possess a typical value that varies widely in the physical versions. For our purposes today, though, it is good enough. The important range of bandwidths for an op-amp are from DC to right around a decade in frequency higher than the point at which the gain magnitude reaches unity, or 0 dB. The general format of an op-amp's transfer function in this bandwidth range is around 2 to 5 poles and 0 to 1 zeros. At DC, the op-amp has a very high gain, between about 10,000 to 100 million volts per volt, depending upon the op-amp in question. For the 808618 SPICE model, when loaded with about 1 kiloohm, we see that the DC gain is about 120 dB, which is equal to 1 million volts per volt, with the output resistance we've set it to. Moving leftward along the x-axis in the direction of increasing frequency, at a very low frequency, the first pole comes into play. Often when discussing transfer functions, we'll talk about something happening before a certain frequency or after a certain frequency, meaning less than and greater than respectively. Here we see that for the 808618, the first pole, called the dominant pole, is right around 23 Hz, based on the point at which phase has decreased by 45 degrees from the flat, very low frequency region. Note that for this specific op-amp, the output resistance I've put on the output affects the DC gain and moves the location of the first pole higher in frequency. But for frequencies beyond the first pole's corner frequency, the loop gain is essentially the same as with the op-amp unloaded. Due to the difficulty in measuring high gain and low frequency, most op-amp datasheets won't show very low frequencies because when the gain is very high, it doesn't really matter what the gain specifically is, as the ideal op-amp equations will be very accurate in that regime. The DC gain is a useful parameter to measure, but after that it's not usually important until the gain gets to around 60 dB. So, after the first pole, there's a very large amount of frequency before the next pole comes into play, as we can see by the phase flattening out to -90 degrees, and gain decreasing steadily by 20 dB per decade of frequency, as expected from a single pole. This particular op-amp transfer function is fairly straightforward, in that there's only one more pole that affects the phase in the frequency band where the gain is greater than 0 dB, and it looks like that pole is maybe around 82 MHz looking at the phase, though other poles might be coming into play at this point, so it's hard to tell. There also don't appear to be any zeros in play. Higher speed op-amps, or op-amps that are trying to get as much bandwidth out of their transistors as possible, tend to have more poles and zeros around the 0 dB gain point. The frequency at which the gain of a transfer function crosses unity is called the gain crossover frequency. For this op-amp, the gain crossover frequency is at around 22.6 MHz. The reason we're so concerned about the number of poles and zeros around the 0 dB point has to do with stability considerations. In order for a feedback loop to be stable, the phase at gain crossover of the loop gain must be greater than -180 degrees. That is, more positive than -180 degrees. We'll discuss this in detail in the next video. So the main features of op-amp open-loop transfer functions relevant to today's video are that they have a high DC gain. They are dominated by a single pole at low frequency, which means that the gain drops by 20 dB per decade for most of the transfer function. And additional poles and zeros start to affect the transfer function right towards the end near the 0 dB point. Now that we've talked about open loop gain, we need to translate this into loop gain for an op-amp with a feedback network. The easiest way to demonstrate this is graphically, as the equations don't really provide much insight. So let's discuss how to extract the loop gain from a given op-amp circuit so we can extract it from some example circuits from LT-Spice. Briefly recalling the general structure of feedback circuits from the previous episode, we know that the loop gain is equal to the open loop gain times beta. We need a way to extract the loop gain from a given circuit in LT-Spice. It's best if we can do this while maintaining the feedback loop, as breaking the feedback loop will often lead to weird nonlinear problems, such as the input offset voltage causing the output to rail when Spice is calculating the DC operating point. So we insert a small AC voltage in series with the connection between Vout and beta, and zero the input voltage signal. Now let's call the voltage signal we've introduced Vs, and we'll call the voltage at the input to the beta block Vin. And then we measure Vout and Vin. Since the summing node has 0 voltage on the plus side, we can see that Vout is equal to 0 volts minus Vin times beta, all multiplied by AVOL. Dividing by Vin to get the gain of this system, we see that the gain of this system is the loop gain times -1, which is what we were after. Note that it doesn't matter what the value of Vs is, since we're measuring the ratio of its effect on the output over Vin. This is effectively what I did in the LT-Spice simulation earlier with a unity gain buffer to extract the open loop gain of the op-amp, since in unity gain configuration, the loop gain and the open loop gain are the same. The loop gain is a little harder to measure in real circuits, though it does involve inserting a voltage in series with the closed feedback loop after a fashion. It's just much harder when you don't have access to ideal floating voltage sources and perfect non-intrusive measurement tools. Now, using this method of extracting loop gain, let's compare the open loop gain transfer function with a gain of 10 amplifiers loop gain transfer function. Here we have two op-amp circuits, one in unity gain configuration and one set up with a non-inverting gain of 10. The 900 ohm feedback resistance on Vn1 is to present the inverting input with the same resistance on the unity gain configuration as seen on the gain of 10 configuration to try to keep everything equivalent but beta. Similarly, the 10K load resistance on the unity gain buffer is to match the 10K load resistance produced by the gain of 10 op-amps gain setting resistors, and the 1K load resistors on both circuits are to ensure that the same output transistor is active, so they have more closely matched characteristics. So using the measurement method we just derived, let's look at the loop gain of these two circuits. The black curve is the loop gain of the unity gain buffer, which is equivalent to the open loop gain, and indeed this is the circuit we used to plot the open loop gain earlier. The blue curve is the loop gain of the gain of 10 amplifier. We see that the gain is lower than the open loop gain transfer function by about 20 dB throughout the entire range of frequencies, which makes sense as the beta value for the gain of 10 amplifier is 1/10, which is equal to -20 dB. Note that the phase looks almost identical, which also makes sense since beta shouldn't change the locations of poles and zeros in the error amplifier prior to gain crossover. The phase deviations toward the higher frequencies are likely due to non-idealities in the input and output impedance of the op-amps, though it's difficult to determine the exact cause. But these non-idealities are only showing small changes in the phase, and only after the 0 dB gain point, and so they don't affect the analysis much. Gain crossover for the unity gain amplifier is about 22.6 MHz as we saw before. The gain crossover for the gain of 10 amplifiers loop gain is about 2.27 MHz, about a factor of 10 lower, which makes sense given that the slope of the transfer function is about 20 dB per decade. So we see that due to the op-amp's open loop transfer function, increasing the closed loop gain will reduce the unity gain bandwidth of the loop gain, that is, the bandwidth at which the amplifier has a gain of greater than or equal to unity, by about the same factor. Though again, for some op-amps, the number of poles at around the gain crossover is closer to 2. And so the reduction in bandwidth will actually be significantly more than a factor of 10 for a factor of 10 reduction in loop gain. Now let's compare the closed loop gain of these two configurations and see how this affects them. Here the only changes to the circuit I made are that we've stopped measuring loop gain and instead are measuring the closed loop gain by applying an AC input voltage to the non-inverting inputs and measuring the op-amp outputs. the loop gain of both circuits is still the same, we're just no longer measuring it. An often used metric for measuring bandwidth is what's called the negative 3 dB point, or the point at which the gain drops by 3 dB from its expected or designed value. This is because for a circuit with a pole in it, 1 decade before the corner frequency of a pole, the gain magnitude of the circuit will decrease by about 3 dB due to that pole. This signals the point at which the gain will start decreasing by approximately 20 dB per decade, if there's only that single pole and no zeros. This metric is useful to use when comparing different circuits or configurations, as it allows the designer to quickly see the approximate relative differences. The negative 3 dB bandwidth for the closed loop gain of the unity gain buffer is 30.6 MHz, and the negative 3 dB bandwidth for the gain of 10 amplifier is around 2.3 MHz. So again, about a factor of 10 difference. Slightly more than that due to the second pole affecting the transfer function slightly right before gain crossover in the unity gain case. So we see that due to the dominant pole, the gain has an approximately proportional effect on the bandwidth of the op-amp. If you set it to a gain of 10, you'll have approximately 1/10 the bandwidth than if you did with a gain of 1. If you set it to a gain of 100, you'll have 1/10 the bandwidth than you did if you had a gain of 10. For closed loop gains closer to unity, this is not as true due to the influence of other poles and zeros, and many op-amps at low closed loop gain deviate significantly from this proportionality, and it is best to simulate them or look more closely at the closed loop transfer function. However, this proportionality is a good starting point. The deviation from the ideal gain that occurs at high frequency is, as we might expect, due to the loop gain getting too small to enforce the ideal gain in the same way we saw in the previous video with the finite gain infinite frequency approximation, which is why the negative 3 dB bandwidths for these two configurations are fairly close to the unity gain bandwidths of their respective loop gain transfer functions. The negative 3 dB bandwidth metric is useful for comparing amplifiers and configurations, but negative 3 dB is actually an error of nearly 30%, which might not be an error you're willing to accept in your system. So sometimes a gain reduction of negative 1 dB is good enough, which is around 11%. However, that's still pretty significant. And so one of the go-to high precision metrics is the 0.1 dB gain flatness, where the gain does not increase or decrease by more than 0.1 dB across the entire bandwidth. This is closer to a 1% error. Now, from the previous video, we know that in order to get a 1% error, you need to have a loop gain of about 100 volts per volt, or 40 dB. So since the loop gain is dropping at about 20 dB per decade, we need to move back about 2 decades in frequency to get around a 1% error. So, taking a look at our simulated data, the negative 0.1 dB bandwidth for the unity gain buffer is around 4.66 MHz, and the negative 0.1 dB bandwidth for the gain of 10 amplifier is around 352 kHz. For the unity gain buffer, this is only about a factor of 4.85 lower in frequency from the gain crossover, and for the gain of 10 amplifier, it's about a factor of 6.45 lower in frequency from the gain crossover, much less than our expected factor of 100. So why is this? Well, in the previous episode, I had infinite bandwidth and treated each transfer function as a single number, but did not incorporate the idea of phase. In reality, phase makes the gain a complex number, which changes things significantly. So let's perform the calculation with complex numbers this time and see what we get. So, grabbing the values from the loop gain plots from earlier, the loop gain for the unity gain buffer at 4.66 MHz is 13.69 dB and negative 92.7 degrees. The loop gain for the gain of 10 amplifier at 352 kHz is 16.18 dB and negative 90.14 degrees. Converting these gain and phase values to complex notation, here are the complex representations of the loop gain at this frequency for both circuits. Now to calculate the closed loop gain, we have our central function using the open loop gain, but since we don't have the open loop gain here, we can just divide the loop gain by beta to get the open loop gain and use this slightly modified version of the equation. So substituting in the complex loop gain values, simplifying and converting to gain and phase, we get a gain deviation of negative 0.1005 dB and an error of 1.15% for each amplifier, which is basically spot on to the gain deviation of negative 0.1 dB and 1.145% error we were expecting. So the equations we used to determine the deviation from the ideal op-amp gain using the real loop gain we learned in the previous episode are still valid. We just need to properly incorporate phase in order to perform those same calculations. Fortunately, phase shifts in the loop gain actually reduce the error in the closed loop gain magnitude. So if you ignore phase, you can overestimate the required loop gain for a given error value during your design phase. One final thing to think about. Notice the phase in the closed loop gain. It is much different from the phase of the loop gain, which is good. However, its value depends upon the poles and zeros of the loop gain transfer function, even when they occur far from the frequency you're looking at, and the phase does change over frequency. If your circuit is sensitive to phase deviations, then you'll need to make sure the bandwidth is higher to ensure that in your pass band, the phase shift is at an acceptable level. And to determine what the phase shift will be, it's best to test or simulate rather than to do straight analysis, as the phase is highly dependent upon the locations of the poles and zeros in the specific op-amp's open-loop transfer function, and computing the locations of the poles and zeros of the closed-loop transfer function is not trivial. That concludes this episode. In this episode, we introduced the op-amp non-ideality of finite bandwidth and explored its implications on the closed-loop gain and bandwidth with different feedback loops using an example op-amp in LT-Spice. In the next video, we will continue with the op-amp non-ideality of finite bandwidth by going over stability in op-amp feedback, and how to determine if an op-amp circuit is stable, as well as discussing the concepts of phase margin and gain margin. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. If you have a question or comment, please leave a comment. See you next time.